All right, let's get started for today. Couple of announcements. Your midterm 1 solutions have been posted onto Piazza. Check that out. Your grades are available on Gradescope. You should be able to see where you lost points with an explanation of why points were subtracted. There's a regrade request window that runs from midnight tonight till midnight on Sunday. So if there's anything you think wasn't graded correctly, submit your regrade request into Gradescope. It'll come in a queue for us, and we'll start looking at it next week. Your homework 6 will be released very soon and will be due on Monday. So pretty short turnaround there. Your project 4 will be released pretty soon too, and will be due next week, Friday at 5. This is a new project, so I know some of you have been kind of looking ahead and solving projects from previous semesters to get ahead. If you did that, you're not ahead for project 4. This is completely new, so make sure to check it out soon. Due next week, Friday. Any questions about logistics? All right, let's dive right in then. Today we're going to cover BaseNet's inference. What was a BaseNet? A BaseNet is a way to represent probability distributions by specifying a directed acyclic graph which has one node per random variable. And then in addition to specifying the graph, you specify conditional probability distributions. One conditional distribution per variable. And the distribution you specify is a conditional of that variable given its parents. From that, if you like to, you can always recover the full joint distribution by effectively multiplying together all of these conditional distributions. So the full joint over all variables x1 to xn in the BaseNet is the product of the conditionals of each variable given its parents. Look at an example. Here is the alarm network, 5 random variables, 1 table for each variable. Every time is the conditional given its parents. And if you want to compute any entry in the full joint distribution, for example, probability of plus b, negative e, plus a, negative j, plus m, you can just pick up all the corresponding entries in the conditional distribution tables, which means 1 entry per table, multiply those together, and that gives you the probability of that specific instantiation in the full joint distribution. All right, here's the BaseNet you'll be working with in your project 4. There will be more than this one, but this will be one of the main ones. So what is this encoding? It's encoding that there's a time of the day, there's a temperature. Based on those, Ghost King will decide what special powers to equip the ghosts with. Those special powers could be laser powers, ultrasonic blast powers, or speed powers, meaning they could go faster. Then based on which powers the ghosts received, which you actually will not know, they will take on a certain form factor. They might have a belt, because carrying the laser or carrying the ultrasonic blast tool might require a belt. They might have a different size, because if they are fast ghosts, they'll be a little smaller, and so the size will be different. Then you will get to observe whether the ghosts are carrying belts or not and what their sizes are in a noisy way. After you observe that, you can run inference. Well, your code will run inference in this BaseNet, and from that infer what type of ghost you're faced with. Then based on having inferred what type of ghost you're faced with, at least likely faced with, you'll not necessarily know for sure, but you'll have a distribution over possible ghosts based on the observation variables at the bottom here. You will then get to use your own special powers. You will essentially want to choose powers to counter what the ghosts chose. So if they have a laser, you actually want to pick speed for your Pac-Man because you can, while you can't literally outrun the speed of light, it turns out the laser can only be used in directions you're currently facing as a ghost, so you can anticipate in which direction they'll be able to shoot in the next turn, and so you'll be able to outrun them because of the fact that they can only shoot in that particular direction that they just moved into at the previous time. If they chose ultrasonic blast, you actually want to choose laser yourself because the ultrasonic blast only has a limited range, and with the laser you can shoot the ghost from further away than they can reach you. And then if they chose speed, you'll want to choose the ultrasonic blast because even though they'll be super fast, once they get close to you, you just blast them away and they go back to their starting position. All right, so that's the base that you'll be working with. Let's take a look at what the game will look like. So here's a video replay of one of the staff implementations. So what you'll see here is Pac-Man's playing with fast. So it has the speed power, the ghosts have the laser power. All right, so Pac-Man won in this case. One thing you'll notice is if you pick the wrong power, you're pretty much guaranteed to lose if you pick the mismatched power in terms of what you should be picking. The power you pick, essentially, you get to hard code that based on the results of your inference. What you'll do in your projects 4 is implement algorithms for BaseNet's inference. Actually, you'll implement inference by enumeration, which we already covered, but not yet covered for BaseNets. You'll implement variable elimination, and for extra credit, you'll implement a sampling-based method if you want to do the extra credit work. The sampling-based method will only cover on Tuesday, so you'll only be able to get to start that pretty late, but everything else you should be able to get started after today. All right, so what we've seen so far in BaseNet is how they can be used to represent distributions, what the conditional independencies are that are encoded by the graph structure. Now we're going to look at probabilistic inference. Today we'll look at these topics here, and then on Tuesday we'll look at sampling. Okay, so what is inference? It's the problem of calculating the answer to a probability query from some quantities you're given. The whole point here is that the quantities you're given initially might not be the quantities you care about ultimately. For example, you might care about the posterior probability of some query variables given some evidence variables, but this specific conditional distribution is likely not provided when the BaseNet is provided to you. You'll get other conditional distributions, just not this one, and somehow you want to turn what you got into an answer to this query. This will be the main query we'll be looking at in this lecture. Something to think about on your own to kind of test if you fully understand what we're covering here is to see if you can turn what we covered today into a similar set of algorithms that can answer this type of query. What is the instantiation of Q that would maximize the conditional probability of Q given the evidence? So it's just a slight tweak on what we're looking at, but it's an interesting thing to just think about on your own if you can turn what we cover into an answer to this. So we've already seen inference by enumeration. That's a very general procedure, right? The way it works is you have evidence variables, query variables, and hidden variables. Evidence variables are the ones for which you know what values they're taking on. Query variables are the ones you're interested in saying something about. And hidden variables are the remaining variables that don't show up in your query, but that are there because when somebody gave you the BaseNet or you learned your BaseNet or specified your BaseNet, they were there because it made sense to have a structure with those variables in it. Okay, so our query would look something like this. What's probability for Q given all the evidence variables? Then our first step in inference by enumeration is to get rid of anything that's not consistent with the evidence, because we know that will not contribute to the final result of what we're computing. Then we sum out over the hidden variables, and then we're just left with a table with entries for the query variables and the evidence. That will actually be a joint distribution between query variables and then the specific instantiation of the evidence. To make that into the conditional, we need to renormalize this table, and we get the conditional for query given evidence. This is something you can apply whenever you're given a full joint distribution, and you're turning that into an answer to this query. So in principle, we could apply this when we're given a BaseNet. We could turn our BaseNet into a full joint distribution and apply this procedure. So for example, we're given this BaseNet here. Our query is the initial distribution of burglary given John called and Mary called. Inference by enumeration says, well, we can write this out as effectively proportional to the joint between burglary n plus j plus m. Then we can write this out as a summation over all the hidden variables of now the joint over all variables involved in this BaseNet specification. Then we write out what the BaseNet is telling us this full joint can be written as, and now we then compute that summation. So this is inference by enumeration. We're doing effectively, when we're looking at this expression here, we're only considering entries in the full joint distribution that are consistent with the evidence. We're summing over the hidden variables, and this here are entries in the full joint distribution computed from what we have in the BaseNet specification. Okay. The number of terms we end up with depends on the number of hidden variables we're summing over. So here we're summing over 2 hidden variables. Each can take on 2 values. So we have 4 terms total in the summation. So we have first one here, second one here, third one here, fourth one here. Now, if your BaseNet becomes a little bigger, and you compute, let's say, the probability distribution for anti-lock, given the observed variables, which in this case would be, let's say, the shaded variables, your summation over hidden variables here will be a summation over, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 hidden variables. So you'd have a summation over 2 to the 13 terms if they were all binary, even more if they were not binary. So you can see, even though we have a compact specification to start out with, once we run inference by enumeration, even though in principle it's always possible, it could get very expensive. It gets more expensive the more hidden variables we have. All right, so why is inference by enumeration slow? Well, effectively what's happening is we are expanding our original BaseNet representation into almost a full joint distribution. We're looking at every entry in a full joint distribution that's consistent with the evidence, which could be a lot of entries. The idea we're going to cover today, variable elimination, instead of first expanding everything and then summing out over the hidden variables, we'll expand by one variable at a time, consider one hidden variable at a time, expand for that hidden variable only, sum out over just that hidden variable, and then repeat. And this way we'll be able to keep around small representations as we go along, at least in most cases, and get an answer more efficiently. Any questions there? So this is called variable elimination. We'll see at the end of lecture that worst case BaseNet inference is still NP hard. So it's not something that will solve all of our problems. But in many cases, NP hard problems have many instances that can be efficiently solved. This is also the case for BaseNets, and so often this will allow us to solve inference problems efficiently, just not guaranteed to always help us solve problems efficiently. Okay, so we'll need some notation first. The main thing we're going to look at in terms of notation is something called factors. So there'll be a whole zoo of factors, so let's start with the first one here. One example of a factor is a joint distribution. It's of the form px, y here. It could be more variables. Essentially, It's a table with entries for every possible instantiation each of these capitalized variables can take on. And those will be the probabilities of that joint instantiation. Okay. A selected joint is another type of factor. Here you take a slice of the joint distribution that's consistent with some instantiation of some of the variables. So here, a selected joint, we instantiated temperature to be cold, and so we get a subset of the entries of the full joint that's shown at the bottom here. Okay. So the number of capitals, something to keep in mind, is the dimensionality of the table. Whenever something's capitalized, our notation means that that variable can still take on any possible value. Once it's lowercased, it refers to a specific instantiation of that variable, and we'll only have that specific entry. Cold here, lowercased, and so everything here for temperature is cold. All right, here's another type of factor, a single conditional. It's the distribution over some set of variables given some other variables instantiated as some value. So in this case, x has been instantiated as small x. The table could look like this for weather given cold. Instead of having a single conditional, you can also have a family of conditionals, where now the thing behind the conditioning bar is also capitalized still and can still vary. And now you'd get a family of what we saw above, so we get multiple of those in one big table here. This one here is sitting right here at the bottom, but then temperature could also be hot, which gives the top two rows. A specified family is one where you instantiate in front of the conditioning bar, but not behind the conditioning bar. So this does not correspond to a probability distribution in and of itself. This is part of a family of conditional distributions, but we sliced it in a way that this is actually not summing to one. This is not a conditional distribution. This is just a subset of the entries where you instantiated what's up front, left open what's in the back. Okay, so in summary, what we'll be dealing with in general is factors. They could be conditional distributions of some set of variables given some other set of variables. Any of those could be instantiated or non-instantiated. Instantiated will be indicated by lowercase, non-instantiated by capitalized variables. Sometimes they have the meaning of a conditional distribution or a joint distribution. Sometimes they're just parts of a joint or conditional distribution that you sliced out of the table and that you retained. Any questions about the factors? Yes?
So is the factor that in the entire table you have in the previous slide? Like what exactly does factor?
Okay. The factor rain given temperature corresponds to this entire table. Another example, the factor weather given temperature corresponds to this entire table here. The factor W given cold corresponds to this table over here. Okay, let's now start using these factors. So let's start with a very simple example here, a BaseNet with just 3 random variables. It could be raining, there could be traffic, could be late for class. Okay, so to fully specify the BaseNet, we need the corresponding conditional distributions. So we have a table for rain, one for traffic given rain, and then one for lateness given traffic. So that's our starting point. Now let's say the query is, what's the probability distribution for lateness? Okay. First we'll look at how we get there through inference by enumeration, and then we'll introduce some tweaks to make it into variable elimination. Okay. So we can express this as the sum over all hidden variables of the full joint between all variables involved here. Now to compute this, we fill in what the BaseNet specifies as what the full joint looks like. So that's this step over here. And now we could compute this. So let's now look at this from a factor perspective. What's going on when we do this? Okay. So we're going to track objects that we call factors. The initial ones are the conditional probability tables, 1 per node. But as we go along, we'll combine them to get new factors. So these are our initial factors. If anything is observed, we go from those initial factors to sub-selecting only the rows consistent with the evidence. So if L equals plus L, any table where L appears, we get rid of inconsistent instantiations. So L appears only in this table over here. So for that table, we'll shrink it to only retain entries consistent with plus L. So this is our new starting point in the case of evidence L equals plus L. Once we have the starting factors, to run inference, we'll start by joining them all together and then eliminating the hidden variables. So just to refer back to the equation here in the previous slide, when I say joining them all together, what that means is this operation over here, we're multiplying together all consistent entries in these factors, which effectively builds a big new table. And then next, we're summing out over the hidden variables, which shrinks that table into the answer to our query. So we'll do exactly that, directly working with the factors now. So joining factors is a lot like a database join. You have two factors which have some variables participating in them. The resulting factor will have all variables that were in any of the original factors, and the table will span then over all values they can all jointly take on. So here's an example. We have two factors. Let's say we join on R, meaning we grab all factors that involve R, which is both of these factors. A join would then compute a new table that has entries for all values that T and R can take on. And in this case, this is what it looks like. We can compute every entry by multiplying together the corresponding entries in the original table. So we get this table over here where, for example, this entry here is the product of this entry and this entry. Keep in mind, this is part of the computation we actually were looking at on this slide over here. This is this part of the computation in the inference, is that first multiplication that we're doing right here. Okay, that first multiplication gives us a factor that corresponds to the joint between R and T. We saw in that calculation we have another multiplication to do, multiplying in the variable that relates to lateness. So we'll be multiplying in lateness given traffic in our next step. So we'll be doing multiple joins here. So we already saw how to join on R, which gave us the joint for R and T. Now we still need to join in this one here. This is a join on T. So we can actually look at the new basenet after we join these two. They're here together in a super variable. We have a new basenet structure. We join on T, which means we look at all the factors that involve T in this resulting set of factors here, which is both of them. The resulting factor will contain all variables that appear here, which is R, T, L, and that's a repeat of T, so only need it once. We get a table over all three of them, where each entry here, for example, this entry here, minus R plus T minus L, comes from corresponding entries in these tables. So minus R plus T sitting over here, and plus T negative L sitting over here. Multiplying those together gives us this entry over here. So what we're looking at on this slide is in some sense the implementation version of the equations we had on the earlier slide where we had a summation and products. In equations here, we're looking at the tables that are actually involved in the computation and what happens to those tables as we do those products so far. Okay, so now we have a full joint over R, T, and L. Next step is to sum out the hidden variables, which are the ones we don't have in our query. So in this case, since we're asking for L, we'd sum out R and T. So this can be thought of as a projection operator. We're actually getting rid of variables in the table. And the way we're getting rid of them is not just by getting rid of the columns that those variables are sitting in, but we're actually going to sum out by looking at the variables we retain and summing together for every possible instantiation of the variables we retain, summing together all consistent entries in the original table. Okay, so here's an example. We have a full joint distribution over R and T. We want to sum out over R. What that means is we just retain T to get entries for the resulting table, which only has T in it. The entries for plus T will come from summing together all consistent entries with plus T. So it'll be 0.08 plus 0.09. And then the entry for negative T will come from summing together the entries consistent with negative T. And here's our resulting table. So any entry comes from summing together the consistent entries in the table we started from. Whenever we sum out, tables shrink. So from a computational point of view, summing out is in some sense a good thing because now we're left with less to pass around going forward, whereas joining is something where we build up something bigger and bigger and bigger, and we need to be careful about. Okay, so here's our running example. We had built up the joint distribution over R, T, and L by joining together the first two factors and then the resulting factor with that last factor. Now summing out over R and T, let's sum out over R first. That means we get a table over just T and L. Each entry in that table, for example, this entry here, plus T plus L, comes from summing together the consistent entries in the original table. Then summing out T, again, same thing. That means T will now be in the resulting factor. We will have a factor just over L, and we get these entries by summing over the consistent entries in the previous table. So for the entry for plus L, we look at this entry, and together they give us the last entry over there. Any question about the mechanics of joining and eliminating? Yes? Yes, it does make a difference if probabilities don't add up to 1 in terms of answering the query that you're asked to answer. In terms of the mechanics of joining and eliminating, it doesn't matter. So for any factor that somebody gives you, whether the entries sum up to 1 or not, you can mechanically go through the procedure of joining and eliminating, and it'll be the same procedure, no matter whether things sum to 1 or not. Okay, so far what we've seen is we've started from many factors. We've joined them all together, which essentially built up the full joint distribution in this case, which is a big table. And then we compressed it back down through elimination to the answer to the query. What we're going to look at now is how to interleave joining and elimination to avoid this full blow-up. Okay, so this is what the picture will look like now. After a join, there will be an eliminate, then there will be a new join, there will be a new eliminate, and so forth. And the structure will be such that whenever you join on a hidden variable, meaning you pick a hidden variable, grab all the factors that have that hidden variable participate in it, join all those factors, and then sum out that particular hidden variable because you now can, because you've combined all the factors it participates in, which now gives you the opportunity to sum out over it. So, mathematically, what does that look like? So, this is our running query. What's the probability distribution for L? If we run inference by enumeration, this is what the math looks like. We multiply together all factors in the basenet. Then we sum over each of the hidden variables to get the answer to the query. In terms of kind of table manipulation, this is a join on R, followed by a join on T, followed by an eliminate on R, followed by an eliminate on T. On the right, what we see is variable elimination. What variable elimination does, it interleaves the joins and the eliminates. So mathematically what's happening here is, starting from this expression here, we notice that for the summation over R, this factor here, L given T, does not have R participate in it. So as you vary the values R takes on, plus R negative R, that factor does not get affected, which means you can actually bring it in front of the summation. And bring it in front of the summation lands it over here. So what we did here is look at these summations and reorganize things that are constant relative to the variables being considered and bring them in front of those summations. Once we do that, Here we have a summation over R, and behind it all the factors that have R participate in it. We do the join on all the factors that have R participate in it. Then we can do the summation over R. And then we can move on to do a join on the next variable, which is t, sum over t. So if you ask yourself the question, why do we need to join all factors that have a particular variable participate in before we can sum it out? This is the explanation, right? The reason we can sum a variable out is that the summation that we're looking at, for example, this one here, needs to consider anything that has that variable participate in it. So as long as you haven't joined everything on that variable, there's no way you can execute that summation. And so in this case, these are the two factors you need to join together before you can sum out over R. All right, so that's the math. Mechanically, what it looks like is as follows. We now first join over R. So that gives us this table over here. We've already done that before. But now, rather than joining on T next, we eliminate R. So mechanically, what that looks like is we sum out over R in this table over here, giving us a distribution for T, probability of plus T, negative T. Now the next step is working with the factors that we have now. We join on T. This gives us a new factor. We know how to get that kind of factor, and then now we decide to sum out over T, and we get the resulting factor here, which is the answer to our query. So that was variable elimination in a mechanic way. What we haven't looked at yet is how to do variable elimination when there is evidence. So if there's evidence, just like in inference by enumeration, we need to start by selecting only entries that are consistent with the evidence. So if we start with these initial factors and the evidence is, let's say, plus R, then we reduce the factors that have R in it to only have the consistent entries, and then we can go through exactly the same procedure as we did before. Now, one thing to keep in mind is once you do this, actually the answer you get from running variable elimination is not yet the conditional distribution. It'll be some joint distribution, and you need to do a renormalization step. So you eliminate all the hidden variables, and then once we get, let's say, the result here would be distribution for plus R, comma L, we need to renormalize that to get the answer to the original query, which is L given plus R. Renormalizing just means add these entries together and then divide every entry by that sum. All right, let's take a short break here, and after the break we'll see some more properties of variable elimination. All right, let's restart. Any questions about variable elimination? Okay, so let's look at the overview of the procedure then. To run variable elimination, what happens is you're given a base net initially, you're given a query, in this case, some query variables Q that you want the conditional distribution of, given some evidence variables E1 through EK. Mechanically, you start with the initial factors. These are the local conditional probability tables, but instantiated by the evidence, so only retaining the entries consistent with your evidence. Then there is a loop. While there are still hidden variables, you pick a hidden variable, then you join all factors that have that hidden variable participate in it. And the resulting factor you sum out over that hidden variable, and then you repeat. Then once all hidden variables have been passed over here, then you end up with a set of factors, sometimes just one, sometimes multiple factors will be there at the end for you. You join all those remaining factors together. What that gives you is, when you're done with this, it'll give you the joint of Q with the evidence. And then you renormalize that joint to get out the conditional of the query variables given the evidence. One thing that you might want to be aware of is when you join factors together, you can ask yourself the question, well, what happens to variables in terms of if they were before the conditioning bar initially, behind the conditioning bar, maybe in both places, one place in one factor, another place another factor, will they end up before or behind the conditioning bar after the join? And the answer to that is, if in any of the factors a variable appears in front of the conditioning bar, it'll appear in front of the conditioning bar in the join of those factors. Otherwise, meaning if it only appears in the back anytime, it'll appear in the back in the resulting factor that you get from the join. Thinking back to BaseNets, the reason this happens is because every variable will appear only once in front of the conditioning bar for its own conditional probability table, right? And it's whenever that thing gets multiplied in that that variable now gets to appear up front, no sooner than that. Little sanity check when you write code, it actually never is allowed to happen that a variable would appear twice in front of the conditioning bar, that you're joining two factors where in both factors the variable is in front of the conditioning bar. If you ended up with two factors like that during your variable elimination, something went wrong somewhere, because that cannot happen. All right, so let's look at another example here, and what we'll do now is we'll start looking at this at different levels of granularity so that we can start thinking about different aspects of the variable elimination algorithm. So here is again our alarm network. We're asked for the conditional of burglary given John and Mary called or didn't call. It's not specified here, but because it's lowercase, we know that it's one of those values and it's fixed. We're not going to be changing it. We know that's proportional to the joint here, and we know that joint is what we get out of running variable elimination, and then at the end we do a normalization step to get the answer to the original query. Here are our original factors. Okay, I'm not writing out the full tables here, but this here should be enough for you to know what part of the full table is present in each of these factors. So we choose A first. We haven't yet talked about why we would choose A first. We'll get to that in a few slides later. But for now, we assume somebody tells us the ordering, and A was specified as the first one to pick. That means we have to pick all factors that involve A, so these three over here. We join those together, which gives us a new factor. And just pay attention to the tracking here. We have up front J, M, and A because they appear somewhere up front here. And then B and E nowhere appear up front, so they stay in the back and are over here in the resulting join. The next step is to sum over A, eliminate it. So we use this factor here. It's our starting point for that. Sum out over A, we get a new factor, which is this one here. In this transition, everything stays where it was in front and the back of the conditioning bar, just A disappears. All right, that's our first variable we eliminated, A. Okay, we're now left with these three factors over here. What are those? It's the two we didn't use yet that were just transferred over, and then these three were used, and instead we're ending up with just this one factor here as a result to substitute for those three original ones. Okay, moving on, starting from those three factors. Next, we're told to choose E. We take all factors that involve E, this one, join those together. If anything appears up front ever, it'll be up front here. So E appears up front here, J here, M here. So those three are up front. B never appears up front, so it stays in the back and appears over here. Then we sum out over E, and we get this factor over here. What are we left with? These two were joined and then summed out over the join, to result in this factor. So we have this one left, and this one we didn't touch, and we also still have. So we're left with two factors. At this point, there are no hidden variables left. Our query was b given j comma m. We've summed out over all hidden variables. We're at the last stage of the variable elimination algorithm. We join together the remaining factors. Okay? And then, to get the answer to the query, we renormalize, which means for this table here, we compute the sum of all entries in that table, call that sum, let's say, z, and then divide every entry in the table by z. And that gives us the answer to the query. All right. Now, we can do the same thing again in equations. It's important to understand the parallel between what we just did, which was a very mechanical view of variable elimination. It's what you would think of when you write code, that you're able to tie this back into the math that's behind it, right? So the math that's behind is as follows. We have a basenet, which is specified by a directed acyclic graph and a set of conditional probability distributions. We have our query over here, and we're now going to just work through the math of computing the answer to that query, and then we're going to pinpoint in the math where the joins are happening, where the eliminates are happening, so you see the correspondence. So, to answer this query, well, we know it's proportional. This sign means proportional to, so that means that the table on the left is equal to the table on the right, up to the fact that you can have to multiply every entry in the table by a constant. That constant is actually 1 over z in many cases, but so this sign here means that, or another way to think of it is that you take the corresponding entries in both tables, you take the ratio between those corresponding entries, and you'll see that the ratio for every corresponding entry is the same number. They're just off by a constant factor. The reason we're okay with doing our derivation this way is we know that if we're just off by a constant factor, at the end of the whole derivation, all we need to do is to normalize, which means compute the sum of all entries to find the constant factor that we need to compensate for this. So even though we're actually computing something different here from what we really want, we know that it's easy to compensate for in the end by finding the normalization constant. All right, so now this marginal here over these three variables can be obtained from the joint, which is our starting point, because we don't have the distribution over those three variables. We only have a specification of the joint. So we can get this from the joint by summing out over the variables that don't appear here. So the joint is over 5 variables. We can sum out over the variables the two that don't appear in the original expression E and A to go from the joint to the marginal over just those 3 variables. Next step is that we can now start reorganizing this full joint over 5 variables by using the assumption that this distribution is not just any joint distribution over 5 variables, it's one specified by this basenet over here. So we fill in that assumption. Okay. Now, we've used the assumption of what our basenet looks like. Next step is to look at how the summation is organized. So we're going to use effectively this property over here. But on the equation on the left, the way it looks is, well, when we sum over E and A, all that matters when we sum over E is factors that involve E. When we sum over A, all that matters is factors that involve A. So we can reorganize this as follows, where we bring the summation over A over here, where these are all the factors that involve A. Anything that involves A cannot be brought in front of that summation because the summation is over A. But everything that doesn't involve A can be up front here. Now, mechanically, what this now corresponds to here is that we're about to do a join of these 3 factors, the 3 factors that involve A. So we join on A, then we sum out over A, which is the elimination step. We end up with this expression over here, where this is the new factor that we just generated. Then we can again look at the summation. We're still summing over E. We can now say, well, which factors involve E? Let's see, is there a typo in there? Yeah, there is a typo. There should be a comma E here. So there are 2 factors that involve E, the 2 last ones. We bring the summation to the back to only involve those two last ones. Again, use that same property, keeping in mind that there is a comma E here. We do a join over E, sum over E. We're left with a new factor, F2. And this is now effectively the answer to our query once we join these together up to normalization. Any questions about how this math corresponds to the more mechanical view of variable elimination? Yes?
What's the F1 again?
Okay, so the notation we use here is just to be able to talk about the factors more easily. F1 here is actually equal to P, J, comma, M, given B, comma, E. But to be able to refer to those factors as the first factor, the second factor, and so forth, we'll sometimes denote them by F1 rather than P. And it also distinguishes them from the original probabilities that were available when we started out. But mathematically speaking, you could just as well write P, F, comma, M, given B, comma, E, as well as F1, J, comma, M, given B, comma, E. They're the same. Any other questions about the correspondence between the mathematical derivation and the mechanical execution of variable elimination? All right, so then let's take a look at an example where we, again, don't dive into the details, but we'll start thinking about what the effect is of the ordering of the variables in which we eliminate things. So here is a query. The query is for x3 given y1, y2, and y3. So the factors we start with are all the original factors from the base net over here. And now we start eliminating in some ordering, right? So if we first eliminate x1, what effectively happens is we compute a factor f1, which is the sum over all values x1 can take on of the join of all factors that involve x1. We get this set of factors over here. Then next, let's say we eliminate x2. This introduces a new factor which we can compute by joining all factors that involve x2, summing out over x2, which gives us this new factor. Then we eliminate z, which is the last hidden variable. Same procedure, join on all factors that involve z, sum over z, and this is our new factor. All right, so no hidden variables left. We join the remaining factors to get this result here. Then if we renormalize, we get the answer to our query. Now, how expensive this all is will depend critically on how large the largest factors that we generate in the process, right? So we generate a factor here, we generate a factor here, we generate another one here, and then one at the end here. So to understand how expensive this is, we need to look at how many entries each of these factors has. So the first one here is essentially joining something that involves two variables, z and x1 are variables there, so it's a factor over two variables, z and x1. If they're both binary, you compute a table here with 4 entries. So this would be a table with 4 entries. Here, the variables are z and x2. If they're binary, again, we'll have 4 entries to compute. Then here, the variables are z and x3, and so we'll have, again, 4 entries. So in this process, the biggest factor we build was a factor of size 4. If we did naive inference using inference by enumeration, building the full joint table first, then we would be building a table with 4 variables. So we'd be building a table with 16 entries, which would be more work than what we did in this particular case. Now, this is still a small example, but the more hidden variables you have, the bigger the difference can be. Let's take a look at a concrete example here. So let's say you're given this type of base net. The query is, was the conditional of xn, which is sitting over here, given all the y variables which are sitting in the bottom row. So these are observed. This is your query variable. Question is, for two different variable elimination orderings, how computationally expensive is it going to be to find the result? So the first ordering for you to consider is this one here. You start with z and then x1 through xn minus 1. The second ordering is start with x1 through xn minus 1 and then finally eliminate z. Those are two options out of, in fact, n factorial options that you can consider for your variable elimination ordering. Let's have you think for a few seconds about which ordering you would prefer and how cheap or expensive each of these orderings is. All right, any thoughts about the first ordering? How expensive it'll be to do that variable elimination? So the question is, what's the biggest factor you generate in that variable elimination with that ordering? How many variables does it have? Okay, let's go through the process. All right, what would happen if we eliminate z? When we eliminate z, we join together all factors that involve z. So which are the factors that involve z? Well, there is the distribution for z itself. Then any variable that's a child of z, its conditional distribution will involve z. So the table for x1 given z will be involved, the table for x2 given z, and so forth, all the way till xn given z. So the first step in this ordering would be a join of pz, with x1 given z, with x2 given z, and so forth, all the way till xn given z. How many variables are there? That's n plus 1 variables. So this join will result in a table with 2 to the n plus 1 entries if these variables are binary. Could be even bigger if they're more than binary, right? I mean, that's pretty much as bad as it's going to get, right? If you did inference by enumeration, you'd build a full join table over all the variables that are not instantiated, which is also n plus 1 variables. So essentially build up the biggest table you could ever build up for this kind of query, starting with z. So that's definitely not efficient. Now let's look at the other ordering, see if it's more efficient. So the other ordering starts with x1. When we join on x1, we look at every table that involves x1. So that's the table for x1 itself here, the conditional, which is x1 given z, as well as the table for any child of x1, which is y1. So we also have here y1, which is instantiated, given x1. So this join involves only two variables, x1 and z, because y1 is fixed, so just two variables. So this will generate a table of the size 2 to the 2. Now, after we did the join and summed out over x1, we're left with our first factor that we generated, f1, which will be for y1 given z. If we now eliminate x2, we need to join all factors that involve x2. Which factors involve x2? Well, this new factor does not involve x2, so no need to worry about that one for the join. Of the original factors, there will be x2 given z and y2 given x2. Just like what we had here for x1, really. Just with the index 1 changed into a 2. So we'll generate the join, which will be a table of size 2 to the 2. We'll sum out over x2, which will result in a factor f2. Factor f2 will just involve y2, which is fixed, given z, which is still a variable, so this will have just two entries. We can keep going all the way through xn minus 1, and every step along the way we'll generate a factor of this type. The number of entries in the resulting factor will be 2 for binary variables, and the intermediate factor you generate will involve xn minus 1 and z, so it'll be 2 to the 2 entries, which is 4. So anywhere along the way here, we only generated small factors. Now we still need to join on z, which was in the original scenario the expensive thing. Now let's think about what happens when we join on z. All these new factors have z in it. So we have n minus 1 factors there that involve z. In addition, we have pz still sitting around that involves z. And we have xn given z. So we'll have 1, 2, and then another xn minus 1 factors for a total of, sorry, not xn minus 1, n minus 1 factors for a total of n plus 1 factors that involve z. But joining is not expensive based on how many factors you join together. It's based on how many variables are involved in that join. So let's take a careful look here. The only variables involved in a join are z and xn, because all the y's are fixed. So we actually only have 2 variables. So the size of the table we generate is a table with 2 to the 2 entries for binary variables, just 4 entries, which is very cheap. Compare that to when we initially joined on z, where it was very expensive. Question there.
So wouldn't F1, so wouldn't F1 include entries for X1 as well, since X1 is joined in both of the 2 probability tables we multiply to get F1?
Okay, so the question is about F1. So what will happen when you join these 2 together? You get something intermediate, which we happen to not call F1. Let's call it F1 prime, which is equal to this. F1 prime, which is over x1 z, but actually z is behind the conditioning bar, and y1 is behind the conditioning bar. Then we'll sum, no, let's see, y is in front, it seems. Let's rewrite this. This thing here would be f1 prime, which would be over x1, y1 is in front, and z is in the back. This would have 2 variables in it, x1 and z, because y1 is fixed. So this would be a 4-dimensional table, or a 4-row table. Now, after you sum out over x1, you'll get this factor over here, which doesn't have x1 in it anymore. x1 will have been eliminated, and we got rid of this variation over x1, when now we only have 1 variable left, which is z. So you are right that there's an intermediate result that involves x1. And so when we look at the computational complexity, in principle, you should look at this one here, and that's why I've been saying it's 4 entries that we need to compute for those, because we have 2 variables, x1 and z. Yes?
Can you explain again what you said about like the y variant? It's not about how many factors or that's
Okay, so let's think about what happens when we join together all factors that involve z at the very last stage here. There is pz, there is x1 given z, and then there is all these factors that we computed, right? If we want to compute 1 entry in that table, so what entries do we need to compute? We need to compute an entry for plus z plus xn, plus z negative xn, plus, negative xn. We need, well, whatever. We need all 4 combinations, right? So you have 4 entries to compute, a plus z plus xn, negative z plus xn, a plus z, negative xn, and a negative z, negative xn. Those are the 4 entries for which you need to compute a number. Now we can look at each of those numbers, how we compute those, right? So let's look at the first one, plus z plus xn. The way you compute is you look at the product of these factors that we circled here, those n plus 1 factors, multiply the corresponding entries together to get the entry in that table. So we'll have a product here of n plus 1 numbers to compute that entry. So the number of factors that participate still comes in some way in the computation. We'll have n plus 1 numbers to be multiplied together. But that's just scaling linearly in the number of factors, right? A multiplication of n plus 1 numbers just takes n multiplications. Any extra multiplication is just additional work that's linear with the number of factors. And so that's very different from what happened if we initially joined on z, where the join on z brings together many, many variables, in fact, n plus 1 variables in a single big factor that's of size 2 to the n plus 1. So your work is exponential in the number of variables, but only linear in the number of factors you join. Any other questions about this? Yes?
Can you explain the last step again, how you got from the factors f1 to fn to the probability of xn given y1 through yn?
Okay, so after you have computed these entries here, where each of these entries will be computed as the product of this one here, and all of these, their corresponding entries, right? You would have a table that expresses the joint between, in this case, you'd have the joint between, well, after you have this table, you'd have something with z and xn. You'd sum out over z, which would result in a table that only involves xn as a variable. And that table will be the distribution for xn, comma, y1 through yn. Now, that is a joint between them. It's not a conditional. You will compute the sum of all entries in that table, then divide every row in the table by the sum that you just computed. That will make all entries sum to 1. That will now be your conditional of xn given y1 through yn. So what we saw here is that it's actually really important to pick a good ordering of the variables. So for one ordering, you ended up with computational complexity 2 to the n. For the other ordering, the second ordering, you end up with computational complexity that's just linear in n, which is very different, of course. Something that scales linearly with the number of variables in your basenet. It's much more palatable to get that to work on large basenets than something that scales exponentially with the number of variables. So we actually need to solve some kind of problem here. Before you start running variable elimination, you need to think carefully about which of the, if you have n hidden variables, which of the n factorial orderings is going to be the ordering you pick such that you get low computational complexity, right? And now, the interesting thing to keep in mind here is that the work we did to compute the computational complexity is actually less than to actually do the computation, right? To compute how expensive it would be to use the ordering z x1 through xn minus 1, we didn't have to actually do the calculation. We just have to say, well, if we first eliminated on z, we would generate a factor of this size, and this would be the variables participating in that factor. And you can actually step through this whole process if you were to eliminate z, then x1, then xn minus 1, and so forth, as shown on the slide, without ever computing any entries, just keeping track of what the tables will be over. And then you can look at many, many of these orderings, hopefully not too many, until you find one where the computation would be relatively cheap, hopefully, and then do the actual computation just for that ordering, right? And effectively what we have here is a search problem, right? You're searching over possible orderings where the cost of joining on a variable and eliminating that variable is its computational cost, which you could count by the number of maybe multiplies and summations you have to do, or simply in a simplified calculation by the number of entries you have to compute the resulting factor. And then you can see which ordering has lowest total cost in terms of sum of number of entries you compute in each step. Question you might ask yourself as well, okay, we now understand this kind of space complexity and computational complexity of variable elimination, right? How good can it really be? Here it worked out really well, for there was an ordering that was very efficient. There were also bad orderings, but there was at least one that was efficient, right? The dominating thing is the largest factor you generate along the way, right? So be careful, especially keep track of that. Previous slide, the largest factor in one case after the summation was 2 to the n. Before summing out, it would be 2 to the n plus 1, compared to 2 or 4 if you use the best ordering. And the question you could ask yourself, if I were to run this search and try to find a good ordering, am I guaranteed for any given basenet and any given query that if I run this search till it finds the optimal solution, and we know how to run searches that find the optimal solution. You could run, let's say, uniform cost search, or if you look at past exams, you could probably find questions that ask you for the design of heuristics for A-star search to more efficiently find a good ordering. Is there always going to be an ordering that results in small factors? Or is it possible that you run this search and the best ordering you find is still one that generates a factor along the way that's really large, right? That's a reasonable question to ask. So the answer is, you're not guaranteed that your optimal solution is a cheap solution. It could be that you're given a BaseNet and every possible ordering will be expensive. Okay? Here's how we're going to show that. So let's say, more generally, we can ask ourselves the question, if you're asked to do exact inference in a BaseNet, you're asked not just to run variable inference, but you're asked to compute the answer to a probabilistic inference query exactly. Can you do this efficiently in all cases? And what I'm going to show on this slide is that there's a family of BaseNets, an example is shown on this slide, for which if you came up with an efficient way of computing the answer to the query, you just proved that P equals NP because you just solved that problem, which makes it extremely unlikely somebody will come up with a general purpose exact inference algorithm for BaseNets. So here's how we show this. The problem we'll look at is how to solve a constraint satisfaction problem, 3SAT, which is a constraint satisfaction problem. In this case, we're trying to see if there is a solution to the problem where we try to assign values to x1 through x7. It could be true or false, each one of them. And we try to find an assignment such that x1 or x2 or not x3 is a true statement, and not x1 or x3 or not x4 is a true statement, and x2 or not x2 or x4 is a true statement, and so forth. Right, so that's what we're going to try to find an answer to. And the way we can answer this question, if we have access to a BaseNet inference engine, is to say, well, we're going to set this up as a BaseNet. And here's what the BaseNet looks like. The top set of variables are the original variables in the CSP. And we assign uniform distributions to them. It's always probability 1/2 to be true, probability 1/2 to be false. Then the next layer encodes these 3SAT clauses. So there will be a variable y1 corresponding to the first clause right here. So y1 is a variable that corresponds to whether the first clause is true or not. So its parents are the 3 variables participating in that first clause, because once you know the values of those 3 variables, you can compute the value of y1. This is actually a deterministic conditional probability table. It's deterministically determined by the parents what the value of y1 will be. Same for y2 and so forth till y8. Now, let's ignore the BaseNet for a second. In principle, we could now say we have all the clauses. Let's define z as the end of y1 through y8. And then z would encode the entire phrasing at the top. The reason we don't jump directly from y1 through y8 to z is because z would then have a big conditional probability table. We have many, many parents. And if you want to make a computational complexity argument, you need to be careful about the original encoding of your problem being small, yet solving it being expensive. And so we cannot rely on conditional probability tables here in our representation that are huge. We need to keep everything small. So I actually have this tree structure thing coming down here where we only end things in pairs, and that way every conditional probability table has at most a small number of parents involved in it. So in this BaseNet here, every conditional probability table involves at most 3 parents, so they're all small tables. Nevertheless, it can encode this clause over here, and if you can answer the query, what's the distribution for z exactly, then you can check whether the probability of z being true is non-zero. If the probability of z being true is non-zero, that means there is some instantiation of the x's that makes everything true. And now you have the answer to your 3-set question. Yes, there exists a satisfying assignment. If the probability of z equals true is 0, that means not a single assignment to the x's will result in everything being satisfied, and we can now say there is no satisfying assignment for the original sentence. And so what we've shown here is that if you can do exact inference in a Bayes net with every conditional probability table in the Bayes net even being small, that would imply you can solve 3-set problems, which makes it unlikely you can do exact inference in every Bayes net efficiently. Right? What that in turn implies is that it's unlikely that you would find a variable elimination ordering that somehow only encounters small factors along the way. In fact, nobody has found one, I guess, for this type of problems, of course. But rather than just being a result about variable elimination, this is a more general result about exact inference in Bayes nets. It's not just saying, oh, variable elimination might not be efficient for all Bayes nets. It's saying any method you can come up with likely will not be efficient for all Bayes nets. Okay? So this is our proof, so to say, that it's unlikely there's a general efficient inference procedure for Bayes nets, but nevertheless we've seen that for some Bayes nets we can do things efficiently, and for some Bayes nets the ordering will affect whether things are efficient or not efficient. So we can ask ourselves the question, right, are there Bayes nets where things are not as hard as they are in the worst case? So here is an example of an easy structure. Just like in constraint satisfaction problems, if your Bayes net has a tree structure, it's called a polytree because it's with directed edges, so a polytree is a directed graph where there are no cycles at all, not even undirected cycles. Remember, a Bayes net can have cycles, just not cycles that you can go through when you follow the direction of the arrows. A polytree cannot have cycles at all. Right? Now, if your Bayes net graph is a polytree structure, then there always exists an efficient ordering. In fact, the example we looked at here is an example of a polytree structure. This is a polytree, and we did indeed find an efficient ordering. There were also inefficient orderings. Now, every ordering is efficient just because you're a polytree, but there are efficient orderings. Something for you to think about to make sure you fully understand how Bayes net inference with variable elimination works is to think about, for some polytrees you draw up yourself, can you find an efficient variable elimination ordering no matter what polytree you draw up? And maybe you can also find inefficient orderings that are not the right choice for that polytree. Now, extensions of this are the following. What if you're given a Bayes net that is not a polytree? You could do something called cut-set conditioning, just like what we saw for CSPs. What's the idea there is, well, it was not a polytree, but if I were to remove some variables from the Bayes net, it would become a polytree. How do you remove variables from the Bayes net? That's something to think about, but effectively what you do is you say, this variable could take on, let's say, 2 values. Then you effectively can make it into 2 Bayes nets, kind of in terms of how the computation would play out. One version where it's the plus value, one version where it's the negative value. Then once it's instantiated a variable, you can effectively remove it from the Bayes net because you can now, at least in a careful way, make sure that you only retain entries consistent with that instantiation, which will shrink some CPTs, will get rid of some edges. And if you do this carefully, and it's not super straightforward, you might want to think about this carefully, how to do this. You can get rid of edges that introduce cycles, and now you're left with a polytree. In that polytree, you'll now run inference twice, once for the positive instantiation of that variable, once for the negative instantiation. If you had many variables, let's say k variables, and if you got rid of those k variables, you'd have a polytree. Then you'd run inference 2 to the k times, once for each possible combination of values those variables could take on. And you then combine the result of those inferences to get the answer to the original query. So how expensive Bayes net inference is, one way to measure it is what's the size of the biggest factor for the best elimination ordering. Another way to measure it, what's the smallest number of variables I need to cut set condition out, so to say, such that I get a poly tree where inference is efficient. It does turn out that both will give you the same answer. The number of variables you need to cut set condition out versus the size of the largest factor in the best ordering will be the same. Okay, so where are we at? We've seen how inference in BaseNet works when you want to do it exactly, but we've also seen that in the worst case, it's NP complete. So if you want an exact answer, you might have to wait really, 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 really long. And so what we'll look at on Tuesday is how we can compute approximate answers to inference queries, such that we can at least quickly get some answer, even if it's not exactly the right answer. All right, that's it for today.